Final Draft Technical Summary IPCC SR Ocean and Cryosphere. Subject to copy edit TS 35 total pages, 38. TS.6 Extremes, Abrupt Changes, and Managing Risks. This chapter assesses extremes and abrupt or irreversible changes in the ocean and cryosphere in a changing climate, to identify regional hotspots, cascading effects, their impacts on human and natural systems, and sustainable and resilient risk management strategies. It is not comprehensive in terms of the systems assessed, and some information on extremes, abrupt and irreversible changes, in particular for the cryosphere, may be found in other chapters. Ongoing and emerging changes in the ocean and cryosphere, and their impacts on ecosystems and human societies. Anthropogenic climate change has increased precipitation, winds, and extreme sea level events associated with a number of observed tropical and extratropical cyclones. High confidence. For example, studies have shown that the rainfall intensity of tropical cyclone Harvey increased by at least 8% due to climate change. 6.3, Table 6.2, Figure 6.2, Box 6.1. In the Northern Hemisphere mid-latitudes, there is low confidence in links between Arctic amplification, blocking events, and various types of weather extremes in recent decades. 6.3. Anthropogenic climate change may have contributed to a poleward migration of maximum tropical cyclone intensity in the western North Pacific in recent decades related to anthropogenically forced tropical expansion. Low confidence. There is emerging evidence for a number of regional changes in tropical cyclone behavior, such as an increase in annual global proportion of Category 4 or 5 tropical cyclones in recent decades, severe tropical cyclones occurring in the Arabian Sea and making landfall in East and Southeast Asia, increasing in frequency of moderately large U.S. storm surge events since 1923, and the decreasing frequency of severe TCS making landfall in eastern Australia since the late 1800s, but low confidence that these represent detectable anthropogenic signals. 6.3. Extreme wave heights across the globe have increased by around 5% over the past 3 decades, medium confidence. 6.3. Marine heat waves, periods of extremely high ocean temperatures, have negatively impacted marine organisms and ecosystems in all ocean basins over the last 2 decades, including critical foundation species such as corals, seagrasses, and kelps. Very high confidence. Satellite observations reveal that marine heat waves have very likely doubled in frequency between 1982 and 2016, and that they have also become longer lasting, more intense, and extensive. Between 2006 and 2015, 84% to 90%, very likely range, of all globally occurring marine heat waves are attributable to the temperature increase since 1850 to 1900. 6.4, Figures 6.3 to 6.4. Both paleoclimate and modern observations suggest that the strongest El Niño and La Niña events since the pre-industrial have occurred during the last 50 years, medium confidence. There have been 3 occurrences of extreme El Niño events during the modern observational period, 1982 to 83, 1997 to 98, 2000, and 15 to 16, all characterized by pronounced rainfall in the normally dry equatorial East Pacific. There have been 2 occurrences of extreme La Niña, 1988 to 89, 1998 to 99. El Niño and La Niña variability during the last 50 years is unusually high compared with average variability during the last millennium. 6.5, Figure 6.5. The equatorial Pacific trade wind system experienced an unprecedented intensification during 2001-2014, resulting in enhanced ocean heat transport from the Pacific to the Indian Ocean, influencing the rate of global temperature change, medium confidence. In the last 2 decades, total water transport from the Pacific to the Indian Ocean by the Indonesian throughflow, and the Indian Ocean to Atlantic Ocean has increased, high confidence. Increased Indonesian throughflow has been linked to Pacific cooling trends and basin-wide warming trends in the Indian Ocean. Pacific sea surface temperature cooling trends and strengthened trade winds have been linked to an anomalously warm tropical Atlantic. 6.6, Figure 6.7. Final Draft Technical Summary IPCC SR Ocean and Cryosphere. Subject to copy edit TS 36 total pages, 38. Modern observations, climate simulations, and paleoclimate reconstruction suggest that the Atlantic Meridional Overturning Circulation, AMOC, has weakened since the pre-industrial, medium confidence. Nevertheless, there is insufficient evidence yet to quantify a likely range of the magnitude of the change. 6.7, Figure 6.8. Climate change is modifying multiple types of climate-related events or hazards in terms of occurrence, intensity, and periodicity. It increases the likelihood of compound hazards that comprise simultaneously or sequentially occurring events to cause extreme impacts in natural and human systems. Compound events in turn trigger cascading impacts, high confidence. 3 case studies are presented in the chapter, I. Tasmania's summer of 2015/16, 2. The Coral Triangle and, 2. Hurricanes of 2017. 6.8, Box 6.1. Projections of ocean and cryosphere change and hazards to ecosystems and human society under low and high emission futures. An increase in the average intensity of tropical cyclones, and the associated average precipitation rates is projected for a 2 degrees Celsius global temperature rise, medium confidence, although there is low confidence in future frequency changes at the global scale. Rising sea levels will contribute to higher extreme sea levels associated with tropical cyclones in the future, very high confidence. Projections show that the proportion of Category 4 and 5 TCS will increase, medium confidence. Such changes will affect storm surge frequency and intensity, and impact coastal infrastructure and mortality. 6.3. Wave heights are projected to increase across the Southern Ocean, tropical Eastern Pacific and Baltic Sea and decrease over the North Atlantic and Mediterranean Sea under RCP 4.5 and RCP 8.5, high confidence. There is still limited knowledge on projected wave period and direction. Accounting for the multiple contributions of waves, tides, storm surges and sea level rise, probabilistic projections of extreme sea levels predict the global average 100-year extreme sea level to very likely increase by 34 to 76 centimeters and 58 172 centimeters, under RCP 4.5 and RCP 8.5, respectively between 2000 and 2100. 6.3. Marine heat waves will further increase in frequency, duration, spatial extent, and intensity under future global warming, very high confidence, pushing some marine organisms, fisheries, and ecosystems beyond the limits of their resilience, with cascading impacts on economies and societies, high confidence. Globally, the frequency of marine heat waves is very likely to increase by a factor of 4,655 by 2081 to 2100 under the RCP 8.5 scenario and by a factor of 16 to 24 under the RCP 2.6 scenario, relative to the 1850 to 1900 reference period. These future trends in MHW frequency can largely be explained by increases in mean ocean temperature. The largest changes in the frequency of marine heat waves are projected for the Arctic Ocean and the Tropical Ocean, medium confidence. 6.4. Extreme El Niño and La Niña events are likely to occur more frequently with global warming and are likely to intensify existing impacts, with drier or wetter responses in several regions across the globe, even at relatively low levels of future global warming, medium confidence. 6.5. Figure 6.5. Lack of long-term sustained Indian and Pacific Ocean observations, and inadequacies in the ability of climate models to simulate the magnitude of trade wind decadal variability and the inter-ocean link, mean there is low confidence in future projections of the trade wind system. 6.6, Figure 6.7. The AMOC will very likely weaken over the 21st century, high confidence, although a collapse is very unlikely, medium confidence. Nevertheless, a substantial weakening of the AMOC remains a physically plausible scenario. Such a weakening would strongly impact natural and human systems, leading to a decrease in marine productivity in the North Atlantic, more winter storms in Europe, a reduction in Sahelian and South Asian summer rainfall, a decrease in the number of tropical cyclones in the Atlantic, and an increase in regional sea level around the Atlantic, especially along the northeast coast of North America. Medium confidence. Such impacts would be superimposed on the global warming signal. 6.7, Figure 6.8. Final Draft Technical Summary IPCC SR Ocean and Cryosphere. Subject to copy edit TS 37 total pages, 38. Impacts from further changes in tropical and extratropical cyclones, marine heat waves, extreme El Niño and La Niña events and other extremes will exceed the limits of resilience and adaptation of ecosystems and people, leading to unavoidable loss and damage. Medium confidence. 6.9.2. Strengthening the global responses in the context of Sustainable Development Goals and charting climate-resilient development pathways for oceans and cryosphere. There is medium confidence that including extremes and abrupt changes, such as AMOC weakening, ice sheet collapse, WACE and GIs, leads to a several-fold increase in the cost of carbon emissions. Medium confidence. If carbon emissions decline, the risk of extremes and abrupt changes are reduced, creating co-benefits. 6.8.5. For tropical and extratropical cyclones, investment in disaster risk reduction, flood management, ecosystem and engineered, and early warning systems decreases economic loss. Medium confidence, but such investments may be hindered by limited local capacities, such as increased losses and mortality from extreme winds and storm surges in less developed countries despite adaptation efforts. There is emerging evidence of increasing risks for locations impacted by unprecedented storm trajectories. Low confidence. Managing the risk from such changing storm trajectories and intensity proves challenging because of the difficulties of early warning and its receptivity by the affected population. High confidence. 6.3, 6.9. Limiting global warming would reduce the risk of impacts of marine heat waves, but critical thresholds for some ecosystems, e.g. kelp forests, coral reefs, will be reached at relatively low levels of future global warming. High confidence. Early warning systems, producing skillful forecasts of marine heat waves, can further help to reduce the vulnerability in the areas of fisheries, tourism, and conservation, but are yet unproven at large scale. Medium confidence. 6.4. Sustained long-term monitoring and improved forecasts can be used in managing the risks of extreme El Niño and La Niña events associated with human health, agriculture, fisheries, coral reefs, aquaculture, wildfire, drought and flood management. High confidence. 6.5. Extreme change in the trade wind system and its impacts on global variability, biogeochemistry, ecosystems as well as society have not been adequately understood and represent significant knowledge gaps. 6.6. By 2300, an AMOC collapse is as likely as not for high-emission pathway and very unlikely for lower ones, highlighting that an AMOC collapse can be avoided in the long term by CO2 mitigation. Medium confidence. Nevertheless, the human impact of these physical changes have not been sufficiently quantified and there are considerable knowledge gaps in adaptation responses to a substantial AMOC weakening. 6.7. The ratio between risk reduction investment and reduction of damages of extreme events varies. Investing in preparation and prevention against the impacts from extreme events is very likely less than the cost of impacts and recovery. Medium confidence. Coupling insurance mechanisms with risk reduction measures can enhance the cost-effectiveness of adapting to climate change. Medium confidence. 6.9. Climate change adaptation and disaster risk reduction require capacity building and an integrated approach to ensure trade-offs between short and long-term gains in dealing with the uncertainty of increasing extreme events, abrupt changes, and cascading impacts at different geographic scales. High confidence. 6.9. Limiting the risk from the impact of extreme events and abrupt changes leads to successful adaptation to climate change with the presence of well-coordinated climate-affected sectors and disaster management relevant agencies. High confidence. Transformative governance inclusive of successful integration of disaster risk management and climate change adaptation, empowerment of vulnerable. Final draft technical summary IPCC SR Ocean and Cryosphere.